Okay, so in today's lecture, we're going to be talking about algebraic extensions. So we start with the definition of an algebraic extension. Let K over F be a field extension then definition. An element alpha in K is said to be algebraic if alpha is the root of some polynomial with coefficients in F. So an element alpha in K is said to be algebraic over F if there is some polynomial with coefficients in F so if there is a polynomial f of x with coefficients in F such that alpha is a root of F. So such that f of alpha equals 0. And we say that the extent that, so an element is algebraic if it's the root of some polynomial with coefficients in F, and the extension is algebraic if every element is algebraic. So we say the field extension is algebraic if every element is algebraic. And one other piece of terminology, if some element is not algebraic, then it's said to be transcendental. So if alpha in K is not algebraic, we say alpha is transcendental. All right. So some examples. So if we look at what is by now our favorite example of a field extension, namely we take K to be f of x quotiented by some ideal generated by some irreducible polynomial. Then alpha defined to be the equivalence class of x is algebraic over F since, as we've seen, f of alpha equals 0 in K. And a non-example, so if we just take K to be now the rational function field f of x, so the field of rational functions px over qx, where denominator, so that's fractions p over q, where q is non-zero, then x So I can consider the polynomial function x as an element of k and it's transcendental. Okay. So proposition. Let alpha be algebraic over f, then there exists a unique monic irreducible polynomial with m alpha equals 0. And we call this the minimal polynomial of alpha. So then there exists a unique monic irreducible polynomial with coefficients in f called the minimal polynomial of alpha, such that alpha is a root of mx. With alpha a root of mx. And secondly, if I take any other polynomial with root alpha, then m divides that polynomial. So if fx is any other polynomial with root alpha, then the polynomial mx divides fx. Okay, let's prove this. So alpha is algebraic, therefore it's the root of some polynomial. Let's pick some polynomial of least degree, and then let's make it monic by dividing by the leading coefficient. So we let mx be a monic polynomial of least degree with alpha a root of m. So all I need to do is take some polynomial of least, so I could always consider the set of polynomials with alpha a root of them, and I can take their degrees. There has to be a minima of the degrees, so I can take a polynomial of least degree then with alpha a root, and then to make it monic I just divide by the leading coefficient. So let me write that down. Notice if f of x is a polynomial where alpha is a root of f of x, then I can make this monic and find a monic polynomial with alpha the root of the monic polynomial by just dividing by the leading coefficient. So if f of x has f of alpha equals 0, then the same is true for the monic polynomial one divided by the leading coefficient of fx. So let me call Cf the leading coefficient of f. Okay. Okay, so let mx be a monic polynomial of least degree with alpha a root. Now the first thing we're going to prove is that if I take any other polynomial which has alpha as a root, then m divides that polynomial. So suppose that I take some other polynomial with alpha a root, then I can apply the division algorithm to divide by m with a remainder. So we get f of x is g of x mx plus rx, and the remainder is either 0 or it has degree less than m. Now if I substitute alpha into this equation, then both f and m have alpha as a root, so r must also have alpha as a root. So r is some polynomial which has alpha as a root. Dividing by the leading coefficient of r, I can make it monic, and then by the definition of m, r must have degree higher than m, but by the fact that in the division algorithm r is either 0 or the degree is less than m, the only way to avoid a contradiction is if r equals 0. So r equals 0 by minimality of degree of m. Okay, so r is 0, and therefore f is a multiple of m, i.e. m divides fx. Okay, so now the only thing left to prove is 1, the uniqueness of M, and 2, the irreducibility. So, okay, so uniqueness is now easy. So suppose we have some second polynomial with the same degree as m, so suppose m x well, let's suppose that m is some other irreducible monic polynomial. So suppose mx is an, so that's not the right way to do it. The next thing we should prove, rather, is that, so let's prove next that m is irreducible, and then let's prove that, so the m we've already defined is irreducible, and then let's prove uniqueness after that. So now let's prove that m is irreducible. So if we have m as some product of polynomials, then I have m alpha, which was 0, equals f alpha g of alpha. This is some equation in K. K is a field, so this implies F alpha equals 0 or G alpha equals 0. So then I would have that F is a polynomial with alpha is a root. So then fx is a poly with alpha as a root. And by definition of M as the unique polynomial, unique monic, as the, well, not unique just yet, but as the minimal polynomial of least degree with alpha as a root, I must have, so I can make f monic by dividing by the least coefficient, and then by minimality of M, I see that I must have the degree of f as being greater than the degree of M. So I will have, in the first case, f alpha equals 0 gives me that f is a polynomial with alpha as a root, and by minimality of the degree of M in the definition, we must have degree of f as being at least degree of M. But then if I see that since M is a product of f and g, this implies that degree of g equals 0, i.e. g is a constant, i.e. g is a constant. It's non-zero constant since M is non-zero, and then it's a unit. Because in the field F, all non-constants are units, and this implies that that M is irreducible, right? So so in the first case, f alpha equals 0, I would get that g is a unit, and likewise g alpha equals 0. Just replacing the symbols f and g implies f is a unit. And since unit in f, and then this tells you that if M is a product of two polynomials, one of them has to be a unit. So this implies that M is irreducible, because I can't write it as a product of two non-units. That's what we just proved. Okay, so M is irreducible, and lastly we should check the uniqueness of M. So suppose M bar is monic irreducible, and the monic irreducible polynomial, and M of alpha equals 0. Well, since M has alpha as a root, we know by what we've already proven that M must divide M bar. So by the above, M bar x equals some polynomial times M of x. So by the above, there exists, I should say it like this, there exists some fx like this. But since M bar is also assumed irreducible, this, and since of course M is not a unit because M is a polynomial of non-zero degree, this implies that f of x is a unit. And then, well, since M bar is monic, this unit has to actually be 1. So since the leading coefficients, so it's some unit in F, and since the leading coefficients, so this is because M bar is irred, since the leading coefficients of the monic polynomials M and M bar are by definition 1, I must have, by comparing leading coefficients, that the unit fx is just 1. i.e. M equals M bar. So there's only one irreducible monic polynomial with alpha as a root, as required. Okay. Okay, so that completes the proof. And now I can make a definition. Let alpha in K be algebraic. With minimal polynomial mx, then the degree of the algebraic element alpha is defined to be the degree of the polynomial mx. The degree of alpha, which I'm just going to write as degree of alpha, is defined to be the degree of mx. The minimal polynomial. Okay, so let's do some examples. So consider our favorite field, f of x quotiented by some irreducible polynomial. Then we saw in previous lectures that the degree of the field extension K over F was equal to the degree of the polynomial P of X. Okay, but so the degree of the field extension was P of X because we had the basis 1 alpha degree of P minus 1, where alpha was the class of X, so the equivalence class of X in K. Okay, we saw that from previous lectures, and now we know that this alpha is algebraic over F because P of alpha equals 0. And in fact, since P is irreducible and has alpha as a root, then when I make it monic by dividing by the leading coefficient, I get an irreducible polynomial with alpha as a root, so it must be the minimal polynomial. So 1 divided by the leading coefficient of P times P of X is the minimal polynomial of alpha, where Cp is the leading coefficient in front of the highest power of x appearing in the polynomial. Just because we know that alpha is a root of P and it's irreducible by definition. So thus, the degree of alpha is the degree of this minimal polynomial by definition of the degree of the algebraic element alpha, right? And the degree of this polynomial is the degree of px, which happens to be the same thing as the degree of the field extension k over f. Okay. So we have these different notions of degree, but in this case, they're lining up as the same thing, and we're going to see that this is not really a coincidence. This is just because K is a field which is generated by alpha. Okay. Okay, so let's make sense of this. Definition. So let K over F be a field extension. And let alpha be an element in K. Then the smallest subfield of K, containing both F and alpha is called the field generated by alpha. If you want to be a little bit more explicit about this, you can say that the field generated by alpha is the field that you get by applying all of the field operations to F and alpha. So I have F, I have alpha, I have all products of elements F and alpha, I have all quotients by non-zero elements, and I have all sums. If you use those operations, so sums, multiplication, division, and subtraction, then that will give you a field containing F and alpha, as well as all polynomials and all, more generally, all rational expressions in alpha with coefficients from F. Okay, so the smallest subfield of K containing both F and alpha is called the field generated by alpha, and we write F alpha for the field generated by alpha. Okay, so just for the future, let me slightly generalize this. So more generally, for any subset S in K, maybe let's say for any finite subset. I think we only need it for finite subsets. So let's say for any finite subset S in K, then the field generated by S is defined to be the smallest field containing F and S. To be the smallest subfield of F of K containing F and S. Okay, so it'll turn out that the field generated by some element alpha, so the smallest subfield containing element alpha, is a very important notion, And the following theorem will tie this into fields of our favorite form. Okay, so let K over F be a field extension and take some algebraic element alpha in K, then we have a more explicit realization of the field generated by alpha. So we can describe this as a field of the form that we've already seen. So the way to make this rigorous is that we have an isomorphism of fields phi from the field generated by alpha actually the isomorphism is going to go the other way around just to be pedantic, so let's write it like this. So the field f of x divided by the minimal polynomial of alpha is isomorphic to the field generated by alpha. Where mx is the minimal polynomial. So since the minimal polynomial of the algebraic element alpha is irreducible, then f of x quotiented by the ideal generated by M is a field, and I claim that this is isomorphic to the field generated by alpha. So this gives us a more concrete, explicit realization of the field generated by alpha. It's just fx quotiented by mx. Okay, and furthermore, this isomorphism acts as the identity on F. Further, the isomorphism phi acts as the identity on F. Proof. Okay. So we're just going to explicitly write down the isomorphism phi, essentially. Okay, so proof. First of all, there is a natural ring homomorphism psi from the ring fx to K defined as such so if I feed in some polynomial px in fx, then psi is just going to sub in the element alpha. So psi applied to the polynomial px is defined to be p of alpha, which lies in K since alpha is in K. Okay, this gives us a ring homomorphism, and since m of alpha equals 0, then psi takes m to 0, so m must lie in the kernel of psi. And more generally, some polynomial lies in the kernel of psi if and only if p of alpha equals 0. But we've seen that this occurs precisely if m divides p. Which is the same thing as saying So this happens if and only if Px lies in the ideal generated by M. So what this tells us is that the kernel is the ideal generated by M. So we have a ring homomorphism psi from fx to k with kernel given by the ideal mx. So what this tells us is that the image of psi is isomorphic to fx quotiented by mx. And furthermore, M is irreducible, so this is a field. So this tells us that the image of psi, since it's isomorphic to a field, it's a field. So it's a field, it's isomorphic to fx over mx. And furthermore, it contains both f and alpha. So by definition of psi, right, well, x goes to alpha, obviously by definition of psi, so the image has to contain alpha. And likewise, it has to contain f, just because it acts as the identity on f. So it contains both f and alpha, and hence, well, the subfield f alpha generated by alpha is a smaller such field, so this implies that f of alpha is an image of psi. But now notice that image of psi consists, by definition, entirely of polynomial expressions in alpha. So by definition of psi, the image just consists entirely of polynomials in alpha. By definition. And all polynomial entries also, all polynomials of alpha obviously has to lie in the field generated by alpha, because any field containing alpha has to also contain all polynomial expressions of alpha. And since every element in the image of alpha is some polynomial expression in alpha, this implies that the image is contained in the smallest field containing alpha, i.e. These two inclusions tell us that the image of psi is exactly the same thing as the field generated by alpha. And that completes the proof. Okay, so we've just, to recap, what we just did is we just gave a completely concrete realization of the field generated by alpha in terms of a field of the form fx quotiented by some irreducible ideal. Okay, corollary. Let K over F be a field extension, and let alpha in K be algebraic, then the degree of alpha is equal to the degree of the field generated by alpha over F. Proof. So this follows by just combining what we've seen before. So we have that F of alpha is isomorphic to F of X, quotiented by Mx. By what we know, this implies that the degree of the field extension F alpha over F is the degree of Mx, by what we've proven in the previous lectures. But by definition of the degree of alpha, it's also given by the degree of Mx, where Mx is a minimal polynomial of alpha. Okay, so this is by definition the minimal polynomial of alpha. So now comparing these two equations, we get the claim that the degree of alpha is the same as the degree of the field extension F alpha over F. So this is telling us that for an algebraic element, we have various notions of degree. We have degree of the field extension generated by alpha, and we have degree of the element in terms of the minimal polynomial, and they're both the same. Okay, so that's very nice. Okay. Okay, so we're running out of time. So let me just end by making a definition and writing down a proposition, which we'll prove next time. So definition. We call a field extension K over F finite if the degree of K over F is finite and proposition all finite field extensions are actually algebraic. So we're going to prove this next time. But let me just make a remark that the converse is not true. So remark. There exist algebraic field extensions which are not finite. So the most famous example is a field of algebraic numbers, which we're going to talk about a lot in future. So let me just define it now, but without really proving anything about it. So an example that we will understand more in the future is the field Q bar, defined to be the set of algebraic complex numbers, so numbers x in C, such that x is algebraic over Q. So this is Q bar, also known as the algebraic closure of Q. So by definition, this is a subset of C. It turns out that it's actually a field. We'll prove it much later. And it's an infinite field extension of Q. but by definition, it's obviously algebraic, because all the elements are algebraic over Q by definition. Okay, so it's true that all finite field extensions are algebraic, and I'll prove it next time, but unfortunately the converse is not quite true. Okay, so thank you.